All right, hello everybody. Welcome to our second stream. Today, I thought it'd be kind of fun to build the solar system in a program called Universe Sandbox. And I actually put me on the camera for one, so that sounds kind of fun too. This is Universe Sandbox. It is a really neat simulation program that lets you basically create and destroy and do all kinds of fun things with the universe, the solar system, the galaxies, all this stuff. It starts off with a basic introduction of the solar system and then lets you do a lot of fun other stuff over time. So this is basically what we got for now. We're going to create this whole solar system from scratch. Probably not a lot of these asteroids and things that you see in here, but definitely the main planets and their orbits, and show just kind of how big the solar system is, how it started out, all that stuff, and talk about each object as we go through it to do a little bit of astronomy. And if we have time at the end, when that's all done, we're going to jump back into Space Engine, which I usually stream with, and go and explore some random planets and galaxies and whatever we feel like doing. So yeah, let's get started. So we're gonna start Universe Sandbox with a brand new simulation, which literally gives you an empty nothing. I'm gonna bring in a little grid so we can kind of get a 3D sense of kind of what's happening. But I love that it starts you out with a galaxy, so you can at least see some cool stuff there. But we're gonna add our sun. We're gonna add our main star here, and the best way to do that is I have to like look around my camera to do this properly, but that's okay. We'll do that there. So we'll bring in the sun, and we'll start with the sun. It is a star, so stars tend to be a little bit bright, right? The sun is a giant ball of fiery gas. You can't really see, but I'll bring up some of the stats about it here. About 702,000 kilometers in radius, actually. So in diameter, it's about 1.5 million kilometers. It's pretty dense. If you took a spoonful of the sun, it would weigh about 5 or 6 pounds. So it's a pretty dense object, right? It's heavy, it's got a lot of mass and a lot of gravity as well. The surface temperature of the sun's around 5,700 degrees. That makes it a yellow-white main sequence star. And it's about just over 4.5 billion years old. The planets came about 150 some odd million years after the sun first formed, with a bunch of debris around it. So that's our sun. It is boiling hot. We can go and zoom in a little bit more and see it actually boiling, and that's one of the cool things that I like about Universe Sandbox is it's really good in the way it renders stars. We are letting time go forward. We can always, if I do it carefully, we can always pause time and not see that, but one of the neat things about looking at a star up close is that you can see that it is constantly boiling, right? These kind of bubbles here, these are called convection cells, and they're constantly, it's hot plasma, which is a very hot gas that all the electrons have been stripped off of. Plasma is a different state of matter, actually, not gas. Hot plasma is moving up slowly through these convection cells, taking heat to the surface, and then that plasma drops back down into the sun. And so you get this kind of constant flow upward and downward in these things called convection cells. What you don't really see on the sun right now are sunspots. There aren't too many of them. Sunspots are these big magnetic storms, almost, these darker spots. But you can't really see many right now because the sun is in a pretty quiet time of its cycle. It goes through an 11-year cycle where it gets more active, more stormy, and then less active and less stormy. But we're just coming out of the less active part and getting into the more active, more intense, more crazy part. So we're going to start to see the sun get more and more interesting. And now things tend to be pretty far away from the sun. The planets are all really far away. So we're going to just go and grab... sorry, I'm losing part of the screen there because it's off my screen, but did that fix it? No, it didn't. Let's go back for a sec. Oh, that's interesting. Okay, I think I'll fix that here. One sec. I want the program to... There we go. It takes up the whole screen now. So I just wanted to make sure that we could use up as much of the screen as we possibly can. So let's go into our planets. We can see all the planets down here. It has a few extra ones too. Other than just the planets of our solar system, 51 Pegasi b is the first exoplanet ever discovered around a sun-like star. So that's a planet around another star, a real planet. It might not necessarily look like this, but we can put 51 Pegasi in orbit of the sun and let it boil because it's way too close right now. I hate to tell you, stars tend to go pretty far away from, or excuse me, planets tend to be pretty far away from stars. So in fact, Mercury, if we start with Mercury, we can kind of see that there's a number that shows you, you can just sort of see the number there. It's actually kind of hard to see right now. I think we might try and bring the UI, make it a little bit bigger. So let's see. Auto scale, but let's make it a little bit bigger. That's nicer. There, now we'll actually be able to see some of these planets a little bit better on the stream, which is kind of helpful. So let's put Mercury in, and so you see that number there. That is the distance that we're getting from the sun. So right now, the sun's pretty big, right? 700,000 kilometers in radius, but 1.5 million. So even pretty close. Mercury's at 80. They're just about 1 million kilometers right now. However, Mercury orbits at 57 million kilometers from the sun. So pretty far. So we're at just about 57 there. And you wouldn't believe that Mercury was actually there, would you? So we're going to add in, we're going to speed things up a little bit so we can actually see the orbit. Because if we make time go a little bit faster, you'll actually start to see the planets go around. Did I pause it? I paused it, so it's going to go really fast. We don't need to. There we go. Yeah, so still really quick. Let's slow it down a little bit. We don't need Mercury going that fast around the sun, but there you go. Mercury actually does go around the sun in about 88 days, or about 3 months, which is not too bad. And this is the distance that it orbits at. So it is pretty close. Mercury tends to get pretty warm, so we're going to pause it just for a sec and go take a closer look in at Mercury. You can see it's boiling quite a bit. Did I get the distance right? 57 million kilometers? You know what? You know what happened? Is I put it in meters. I gave it 57 million meters, which is fine, but that's about 1,000 times closer than Mercury actually is. And so if we go and we take a closer look at Mercury now, a lot of it is boiling off into outer space because the sun is so hot. It's just getting melted. And if we take a closer look at Mercury's info, the temperature of it right now, 1,089 degrees. That's just way hotter than Mercury ever should get. So yeah, I wouldn't worry about that too much. But we're gonna, well, leave it to me to do the first thing absolutely wrong. That's okay. We've got the sun in the right place, which is anywhere. So we've got the sun there. Let's try it again. Let's try and get Mercury in the right spot. We're gonna add the planet Mercury. Okay, so now we're in kilometers. Yeah. So see, it was in meters before. We want 57.9 million kilometers. So we're going to have to go a bit further. And the grid kind of gives you a bit of help there. There's 10 million kilometers right about here. Here it is. So we're going to 57.9. Too far. 57 million kilometers. 57.9. That's pretty close. There we go. That's a bit better. Now if we let time go forward, we can actually speed things up a bit because Mercury does go quite a bit faster. Or not quite a bit slower, I should say. And if we just want to focus on the sun a little bit. So there we go. There's Mercury going around the sun. We can also bring up the orbit, which is kind of nice right now. We'll get rid of the grid so we see it a little bit nicer. There you go. We have one planet in our little makeshift solar system. That works out pretty well. There's nobody in chat right now. That's okay. We'll see if there's any. I got a couple viewers. That's cool. All right, so there's Mercury flying around the sun at 57 million kilometers away. And now we'll pause and actually go and take a closer look at it. So here it is. So let's see. Let's learn a little bit about Mercury as we zoom right in. All right. So one of the first things to know about Mercury is that it does look a lot like the moon. It's bigger than Earth's moon, not by a lot. The Earth's moon's about 3,500 kilometers, and we can actually add, if we bring in Earth's moon, you can kind of see how big the moon is right there. So this is Earth's moon compared to Mercury. A little bit smaller than the planet Mercury, but lots of craters, right? Mercury's got a lot. But the biggest difference between Mercury and the other planets is that this isn't quite correct. It's actually about 80% solid iron on the inside. About 80% solid iron. It's basically a big ball of iron surrounded by a little bit of rock. Okay. And I don't know how we ended up back at the sun. Where's the Mercury gone? There it is. So that's kind of the composition of Mercury is mostly iron with kind of a rocky outer layer. And so this rocky outer layer has been, pockmarked a lot by ancient bombardment of asteroids and comets and all kinds of crazy things. The really interesting thing, the Messenger spacecraft, when it went past Mercury, I gotta find out when that actually was, but when Messenger went past Mercury, Messenger spacecraft, there we go. Yeah, there you go. Oh, up until 2015. Between 2011 and 2015, Messenger actually did a lot of really cool science. It mapped the entire surface, and one of the amazing things that it really did was that it figured out that there are actually pockets of water on the South Pole in some of these craters down here. They're not mapped very well, so it looks a little bit weird in this image, but in the South Pole of Mercury, you actually have craters with ice water. And if Mercury, the closest planet to the sun, can have ice water, any planet can have water, which is pretty amazing. So you might think Mercury is really hot. It is. On the surface, you can see the temperature here, 156 degrees Celsius. That's the average temperature. In the daytime, when Mercury's facing the sun, it gets up to about 350 degrees Celsius. It gets really, really hot. Sunlight is really powerful on Mercury because it's really close. But at nighttime, on the dark side of Mercury, it gets really cold. It goes down to minus 150 degrees Celsius because there's no air, there's no atmosphere. If Mercury had an atmosphere, it could trap some of that heat. But basically, all the sunlight bounces off the rocky surface and back out into outer space. Some of it does get absorbed, and that heats up the rocks a little bit. But most of it bounces off in outer space. And so when it becomes nighttime, the cold, dark outer space, which is on average about minus 257 degrees Celsius, really, really cold, that cools down really, really fast. So Mercury gets really cold at night. It also has kind of a weird orbit. Although it orbits around the sun every 88 days, it actually rotates every 57 days. And so that's kind of every 2 orbits, it spins 3 times, which is kind of a weird resonance. All right, and you can kind of see that as we let it go here. We're going to focus on the sun so we can see Mercury working its way around in a nice stable orbit. Okay, so that's Mercury. The next planet we have to add is going to be Venus. Now Venus is 108.2 million kilometers away from the sun, so quite a bit further. So we're going to zoom out a little bit more. Oh no, I've done it. Oh yeah. Okay, so I did that wrong. That's okay. We're going to delete that because we can start again. This is the great thing about Sandbox, Universe Sandbox, is that you can just make things again and again and again. So Venus, we're going. We don't want astronomical units, really. We want. All right, so 108.2 million kilometers, right about there. All right, so that is Venus. And if we let it go, you can see already that planets that are farther from the sun orbit slower. Okay? It's conservation of angular momentum that a planet closer to the sun goes faster, a planet farther away is going to move slower. And so Mercury in 88 days orbits the sun. Venus takes about 227 days. And you can see that in some of the motion data. So 226. I was off by a day. So 226 days to orbit. But here's the crazy thing about Venus. Actually, there's several crazy things about Venus. So we're going to pause time for a sec as we go in and take a closer look at the planet Venus. Venus is actually the hottest planet. It's the hottest planet. And you might be thinking, well, why? I mean, Mercury is so much closer to the sun. You can see Mercury's orbit, and there's Mercury over there. Mercury is so much closer to the sun. Why is Venus the hottest planet? Well, Venus has clouds, right? It's got really thick clouds made of carbon dioxide. And so Venus traps all that heat from the sun. And so on a normal day, you can already see the average temperature of Venus over here, about 461 degrees Celsius, really, really hot. So Venus gets like smoking hot, and it stays smoking hot because at nighttime, all those clouds trap the sunlight, the heat from the sun, and a lot of it does not get lost into outer space. Venus actually has what we call a runaway greenhouse effect. So its clouds are thick carbon dioxide, the same stuff that acts as a greenhouse gas here on Earth, keeps Venus very, very warm all the time. So on Venus, the atmosphere is really thick. If you were on the surface, it'd be like being 100 meters below sea level on Earth. You'd be under the ocean. Oh no, that's not quite right. It's 100 atmospheres, almost 100 atmospheres of pressure. And I think you're actually able to see that surface temperature, energy. So it's nice that it gives you all this information as well. Atmosphere, there you go. Surface pressure is, if you can see that behind my head, surface pressure is 91 atmospheres. So 91 times the atmospheric pressure of Earth, which is really, really thick and heavy. You wouldn't be able to breathe that, of course. Not just because it's carbon dioxide, but because it's thick and hot and heavy. Crazy place to be. But Venus also has some really weird things going on with it. We think that a long time ago, Venus got hit by an asteroid or a comet or something because it actually spins slower than it orbits. Venus actually takes, so we said 226 days to orbit the sun. 226 days to orbit the sun. It actually takes about 248 days to rotate. So if we look here, its orbital period, the time it takes, 1 year on Venus, 226 days. One rotation, there you go. Its rotational period is 243 days. That's a day. So long story short, it means that on Venus, a day is longer than a year, which is pretty crazy. Pretty crazy. And it's the only planet where that's true. Well, sort of. We'll talk about some other ones as we go a bit further out. So that's Venus kind of in a nutshell. We're going to go back to focus on the sun as we make the Earth. Now the Earth is, hopefully you know, is about 150 million kilometers from the sun, or 1 astronomical unit. 1 astronomical unit. That is the definition of an astronomical unit. It is basically the distance between the Earth and the sun. So we'll drop the Earth right there. Excuse me. I've been talking a lot today. Got some water. So there's the Earth. And if we take a closer look, we can see all the planets working their way around. Our time scale right now is 3 days of time. About 3, well, let's actually set it to 5. So it's about 5 days for every second of time that we experience. So there's 5 days happening here. And so the Earth slowly rotates as well. Earth is at what we call just the right distance. We can actually bring up the what's called the habitable zone of the sun. The habitable zone of a star, or the Goldilocks zone as it's often called, is the green zone here. That's the zone where the temperature is just right for liquid water. If a planet is too close to the sun, like Mercury or even Venus now, you couldn't have liquid water on the surface because it would just boil away, it would evaporate. Although we already said Mercury has some ice water at its south pole. That's because that part of the crater that has the water never gets direct sunlight, so it can never melt or sublimate or boil or anything. So But Mercury can't have liquid water. Venus is probably too hot to have liquid water anyway, but it could have been, a long time ago, could have been habitable because the sun is actually getting hotter over time, which means the habitable zone of the sun is actually extending outward. So a long time ago, several 100 million years, this green zone, the good zone, the Goldilocks zone, was probably quite a bit closer, and Venus would have been part of it. Okay, so now Earth is in the habitable zone. We'll talk about Mars next, and you'll get a sense of where that is. But here's our Earth, the place we live. It's spinning really fast. We're going to stop it so we can actually take a nice look at the Earth. The Earth spins every 23 hours, 56 minutes, 24 hours, right? It slowly works its way around the sun once a year, 365 days and a quarter. And because Earth is tilted relative to the sun, about 23.5 degrees, notice that the solar system planets are all flat. They're all in this flat plane. I didn't just build it this way for the sake of it. All the planets in real life are actually on this flat plane. None of them go really far above or below this flat part of the solar system. But they can be tilted. And so Earth is tilted 23.5 degrees to this orbital plane. And that gives rise to the seasons because at certain times of year, this tilt points out this way, and that gives the southern hemisphere more direct sunlight. On the other side of the year, the tilt points directly this way, and the northern hemisphere gets more direct sunlight. So that's why we have seasons. It's not about getting closer or farther. Believe it or not, the closest the time of year when the Earth is closest to the sun is actually January. So even though it's freezing cold winter in Canada, where I live, that's when the Earth is closest to the sun. Go figure. All right, so there we go. So that's our Earth. Nice place. 365 days to go all the way around in the habitable zone. Lots of seasons, lots of life, lots of great people. I spend most of my days there, as you can imagine. All right, let's add Mars. Okay, the red planet Mars. Mars is 227 million kilometers. Now I actually have to look at it in astronomical units. So AU distance Mars to Sun is 1.52. So it's 1.5 times farther from the Sun than the Earth is. So we can add Mars. 1.52 AU, so 152, right about there. Perfect. So that's Mars. We want to focus on the sun so the planets don't run away from us. Okay, so there's Mars. We're going to get rid of our menu down there so we have a nice view of it. And again, if we look over top of the solar system, I'm going to speed time up a little bit. You can see that planets closer to the sun do in fact move faster. Mercury goes fastest, Venus second fastest, Earth third, and Mars takes about 687 days to orbit the sun. It's quite a bit colder because it is farther, so here's the motion. You can see orbital period is in years. If we move it to days, you can see 686. I'm always off by 1. I don't get it. That's just the way it is. In astronomical units, it's semi-major axis in not suns, Jupiters. We want kilometers. Yeah, 2.278 million kilometers. There we go. Okay, so that's Mars. Let's pause for a second. Mars actually is similar to the Earth in a lot of ways. It spins, its rotation period is a little bit longer, so a day on Mars is like 26 minutes longer than a day on Earth. Not a big difference, but it does make a difference when you're trying to run a robotic spacecraft like the rovers over there. Mars has some really interesting features. It has the tallest volcano in the solar system, which is right here. This is called Olympus Mons. This volcano, it is a volcano. It's dormant. It's not erupting or anything, but this is about 3 times as tall as Mount Everest and 10 times as wide, which means it's got a very thin slope. So you can actually imagine walking up this mountain. You literally can walk up it, and it's just kind of a gradual slope. It just goes on for a really long way, and then eventually does pull you up above the atmosphere where you can't breathe. And even if you were below the atmosphere on Mars, you can't breathe anyway. Its atmosphere is mostly carbon dioxide. We call it the red planet because of this red, rusty color, and sure enough, it is because of rust. There's iron oxide covering the surface. Oxidized iron is rust here on Earth. When you see an old piece of metal get rusty, that's what's happening on Mars. And so the surface of Mars is actually reddish because of that. But if you could dig down underneath that soil or sweep away all that red dust, underneath you would find rocks that are the same color as rocks on Earth. Earth rocks are exactly the same color, gray, brown, sandy. Mars does have water as well, just lots of water, but most of it's hidden beneath the surface. Yeah, we don't need to do that, thank you. It's got a small core of iron, just like the Earth and the other planets, but yeah, Mars's water, most of it is frozen underneath the surface as a giant glacier. There is some surface water, as the rovers have found, but if there is still life on Mars, it doesn't live on the surface. Chances are it's small bacteria that live underneath the surface. And the next rover, the Mars 2020, which is called Perseverance, I believe, is going to be going up in about a month's time to go and take a closer look and see if there actually was life on Mars in the past. We know that there's the possibility for Mars to have had life, but it hasn't been confirmed yet, so hopefully we get there. But Mars also has a tilt of 23.5 degrees, so it has seasons, just like the Earth. Of course, its seasons last a little bit longer because it does take 687 days, almost 2 years, to orbit the Sun. So there we go. There's all our planets. Now things start to get a little crazy when we get out to Jupiter, because Jupiter is, for one, the biggest planet in the solar system, but more importantly, it's further. It's where we start to differentiate between the rocky inner planets and the gas giants, the outer planets. So Jupiter is 5.2 astronomical units away, which puts it at 778 million kilometers. That's all. 5.2 astronomical units. Cool. So big difference now, and you might realize, or you might know this already, that the gap between Mars and Jupiter is where the asteroid belt resides. Now I think we can actually make an asteroid belt, because why not? Let's give it a try. Ring, ordered ring, asteroid belt, and we want to add the asteroid belt to the Sun. There you go. Look at that. So we're going a little bit further here, and actually no, I don't want to do that now. Okay. There we go. So we actually have an asteroid belt now between Mars and Jupiter, which is exactly where it should be. So if we can we'll fly around a little bit. A little bit of free flight here. We can see all these little asteroids kind of puttering around. Hopefully you can see all of those. We'll go in a bit closer, and we can see them flying at us. They're not very bright, but they're all there. They're all moving around. And they orbit between Mars and Jupiter. If you took all the mass of the asteroids in the asteroid belt, you can actually see them contrasting against the galaxy there. If you took the mass of all the asteroids in the asteroid belt, it would make a planet that's pretty small, probably a bit smaller than Mars. But it was thought that there might have been a planet that tried to form in between Mars and Jupiter. But because Jupiter has so much gravity, it's so big, Jupiter's tidal force, its gravity, pulled apart whatever was there and left us with these smaller asteroids. Jupiter also has about 79 moons. I say about, exactly, as far as we know, 79 moons. 79 moons, that's a lot. Earth has 1 moon, which we didn't actually add. I suppose I should have added it, but Mercury and Venus don't have any moons. Mars has 2 tiny moons, Phobos and Deimos, the little tiny ones. Funny thing about Mars's moons, Phobos and Deimos mean fear and panic. So perfect names to go with the god of war of Mars, right? Jupiter's moons, though, have a lot of different names, a lot of different gods and goddesses. Jupiter in mythology was the king of the gods. In Roman mythology, that'd be Zeus in the Greek. But a lot of the main moons were named after wives of Jupiter in the mythology. Jupiter has 4 large moons. They're called the Galilean moons. That's Io, Europa, Ganymede, and Callisto. And if we take a look, you can actually see, we'll just put them in. We're not going to get the distances right, but Io is the closest. Europa, Ganymede is the biggest moon in the solar system. And just to put things in perspective for you, if we look at Ganymede up close, there it is. Ganymede compared to Earth's moon is quite a bit bigger. So you can see Ganymede quite a bit bigger than Earth's moon. We'll delete that for now. We don't want too many explosions just yet. So there's the moons going around. Okay, now I did it. So yeah, unfortunately, all those we had the moons too close to Jupiter, and they all started destroying, flying out into outer space as fragments. I wonder if I can delete those fragments. Yeah, let's get rid of a bunch of them. So Jupiter is the biggest planet in the solar system. I'm gonna try and get rid of all these fragments now. And it's huge. It's a lot bigger than the Earth. It's a lot bigger. It is the biggest planet. It's not heavy enough to go anywhere near becoming a star. So there's no real worry of that. Wow, that piece got... Holy smokes. I'm zooming out because I want to see where this fragment got shipped to, but apparently it's being flung right out of the solar system. So let's go in close and make sure we can delete that before it goes flying. Might have been what's left of Io. Yeah, there you go. But, oh, okay, so Io got destroyed, but look, Europa, Ganymede, Callisto are all doing okay. Well, for now, I think Europa's going to get destroyed. So let's just get rid of them. But if we... Okay, there's Jupiter. So we'll go a bit closer and take a look at Jupiter, the biggest planet in the solar system. Lovely view. We got the big red spot over here. The great red spot is a hurricane that is twice the size of the entire Earth. And if we... I can actually show you that it is twice the size of the Earth. We're going to add in the Earth right next to Jupiter here. Oop, there it is. And let's go in nice and close so we can see it. There, that's about how big the Earth is next to Jupiter. 1,000 Earths would fit inside Jupiter, and you can see the gray red spot's about twice the size of the Earth. It's a pretty huge planet. It is made of gas, mostly hydrogen, helium. A little bit of the brown clouds are ammonia, and there's a little bit of other stuff in there too, argon, methane, some of those things, but mostly hydrogen and helium. We can see it spinning pretty quick. Jupiter does spin really fast. It's the fastest spinning planet. It rotates in just 9 hours, I believe, 9 hours and 50 minutes. So let's actually take a look and confirm. Period. Yeah, it takes almost 12 years to orbit the sun. It is pretty far away. Its rotation, there you go, 9.9 hours, just under 10 hours for Jupiter to rotate completely. But Jupiter is thought to have kept our solar system together. Jupiter might be one of the main reasons that there's life on Earth, because ancient asteroids that were flying around the solar system that would have crashed into Earth and stopped any life from forming, from being able to survive, the solar system might have thrived because Jupiter deflected all of those rocks, right? Those ones that would have destroyed Earth were deflected by Jupiter, and so Earth was able to develop life because of that. We won't really know that until we go and take a closer look, but it's kind of cool, right? Kind of cool to think about that. So that's Jupiter, and it's pretty far. We're already at 778 million kilometers. 5.2 astronomical units, right? Remember, an astronomical unit is the distance between the Earth and the Sun. I'm going to bring up the habitable zone again, because now we can see that Mars is in the habitable zone, which means Mars can have liquid water on the surface. A planet like Jupiter is far out of the habitable zone. Any water would freeze into ice. That's what the blue means. And so every star has its own habitable zone. Based on how bright, how big the star is, right? A hotter star, that habitable zone is going to be further out. A colder star, it's going to be closer in. And so in our habitable zone, technically Earth and Mars are in our Goldilocks zone, our habitable zone, but Venus used to be. So Mars was a lot colder. And actually what's interesting about Mars is that as the habitable zone of the Sun moves outward, because the Sun is gradually, very slowly heating up, Mars might become a better and better and better place for life. You know, right now the average temperature of Mars is cold, minus 63 degrees, but it can get warm sometimes. But if Mars does end up moving in, once it does heat up, because the Sun heats up, millions of years down the line, hundreds of millions of years down the line, Mars might be a better place for life, which is kind of exciting. All right, let's go take a look at Saturn. Unfortunately, we're not going to get Saturn's rings right away, but I'm actually going to just look up Saturn's distance to make sure we get it right. So the Saturn distance is 9.5 astronomical units. 9.5. There we go. Boom. And there we go. Now we have Saturn. So quite a bit farther than Jupiter, not twice as far, but a lot further. Saturn orbits in about 30 years, so it's really far compared to Jupiter, 12 years. So one Saturn year is 30 Earth years, which is a long time. So we're going to speed things up a little bit more, and we'll start to see, you can really start to see the inner planets kind of working their way around. I guess when we zoom out far enough, it shows the asteroid belt. We don't need the habitable zone anymore, but you can see all the asteroids kind of working their way around pretty quick. So Saturn is a lot like Jupiter. It's cold. It's a gas planet. It has more moons than Jupiter now. It didn't used to, but recently some more were discovered. Saturn actually has 82 distinct moons, and we're going to have to give Saturn its rings because they don't start with it naturally. It is also made mostly of hydrogen and helium. And let's add in the rings. Saturn's rings. Add Saturn's rings to Saturn. There we go. See, this is the downside, is the particles. It really starts to weigh on the system, but that works. You can see them all spinning. And that kind of highlights the fact that Saturn's rings are made of little bits of ice. Excuse me. Jupiter, as we actually show here, Jupiter has rings as well. They're just a lot darker, a lot smaller, and a lot less icy, a little more dirty. So Saturn's rings are very visible because they're big, they're bright, they're made of ice, which means they reflect light very well. And so that's basically Saturn in a nutshell. And the rings are tilted, you can see as well. And the cool thing about that is that at certain times of year, over the 30-year cycle of Saturn, that tilt will face the Earth and make the rings really nice and bright in photos. But occasionally, of course, it means it's edge on as well, and we get to see basically this, where you can't really see the rings of Saturn. And so that varies over the 30-year period of Saturn. It is quite a bit colder, but it's big. It weighs 95 times the weight of Earth. So it's pretty big, pretty heavy. So that is Saturn. We're going to let time keep going. Saturn with its 82 moons. Some of those are really interesting. There's Titan. Titan is the second largest moon in the solar system, and it's the only place that has an actual liquid cycle, which is kind of cool. I'm going to show you Titan here. Let's go and take a look at Titan next to Saturn. So we're going to pause, go in and take a look at Saturn. We're losing little bits of ring, but Titan is small compared to Saturn, but is one of the moons. Let's go and go equatorial so we can see it up close. There we go. So Titan, it isn't this close to Saturn, but it gives you a sense of the size. Titan is the only other moon in the solar system with a liquid cycle, but it's not water. It rains. There are lakes, several lakes on Titan, but they're not made of water. They're made of methane and ethane. Basically, gasoline is what Titan is its atmosphere is made of. Its liquid is made of. So a really interesting place. We've sent the Cassini probe and the Huygens probe to Saturn, and Huygens actually dropped onto Titan and landed. And that's really awesome that it did that. Learned some really cool things. So that's Saturn. Saturn's rings are slowly going to disappear. As you can see, as time goes on, the bits of ring are leaving in the simulation and going into the outer solar system. All right, our next planet. We're almost there. We have everybody's favorite planet to say. Uranus. I don't care. I'm used to it. I work with kids, right? And so they say Uranus all the time, and they laugh, and it's great. They have fun. I'm totally numb to it at this point. So Uranus is 19.8 astronomical units away, a lot further than Saturn, almost twice as far as Saturn, right? It's really far, and this is why Uranus and Neptune are called ice. Look at all the bits of Saturn's rings flying off of it there. Uranus and Neptune are called ice giants. They're called ice giants. Pause time. Let's go and take a closer look at the ice giant, Uranus. Uranus is a little bit smaller than Saturn. It's kind of what you would call super Earth size. But you see this really interesting kind of ring on its side. You know, if we put Earth next to Uranus, you can see how big the Earth is. Whoop, I have a little trouble working our way around here. So there's Earth next to Uranus. It's a big planet, right? About 14.5 times the weight of Earth. Pretty big. Uranus actually has rings as well. And if we bring them in, you can't really even see it. It's there. It's just this little thin, tiny ring that's not very bright. You can kind of see it against the background of the galaxy there. But notice that the ring is actually over top of Uranus, spinning around like this, orbiting like this. And that's because Uranus is actually tilted 90 degrees to the rest of the solar system, which means that as Uranus orbits, as it goes around the sun, let's actually show. So it goes around the sun. Its south pole right now is facing the sun, and as it works its way around, eventually on the other side, its north pole will face the sun. And when it spins kind of like it's a rolling ball along its orbit. So when it's facing the sun, it's actually spinning like this. And you kind of get that sense when you look at the south pole here. It's spinning like this. So 90-degree tilt, and that tilt is similar to Venus, where we think that a big asteroid came and crashed into that planet and tilted it on its side, and that's why it rolls around. But because of that tilt, it's got some very interesting weather. It's got different storms, and it's a really unique planet to study in our own solar system. There's no chance of life being there. It's hydrogen, it's helium. Uranus has 27 moons. They're mostly named after Shakespeare characters, which is kind of neat. But other than that, we don't know much about Uranus because the only spacecraft to ever fly by both Uranus and Neptune was Voyager 2 back in the 1980s. And all it could do was fly by. So there's so much still to learn about Uranus and Neptune being in the outer solar system. So let's go and add in Neptune. So Neptune, how far is Neptune from the sun? Pretty far. It's cold. It's the other ice giant, 30 astronomical units. So I think, what did we say? Uranus was 19. Neptune, not twice as far, but pretty far. Oh, geez. No, that's too far. Too far. 30 is right there. So there we go. Let time go forward. Now you can see that, if we like just look how far away Uranus and Neptune are. Like, we go into the inner solar system now. You see Mercury, Venus. Oh, I stopped time, didn't I? Mercury, Venus, Earth, and Mars. Right, we want to speed up a little bit. Oh, the simulation can't run any faster because I have too many rings. That's okay. But you see Mercury, Venus, Earth, and Mars going pretty quick, working their way around. Remember, 1 year is the time it takes the Earth to orbit the sun. And so, the outer planets are going pretty slow. You can barely see Neptune even moving. But if we go up to Neptune, Neptune is another ice giant similar to Uranus. It is very cold, right? Minus 227 degrees Celsius. But Neptune, like Uranus, is made mostly of hydrogen. It does have some methane, which gives it that bluish color. It is a beautiful looking planet. It doesn't look like it has a lot of features, but a long time ago it did have a spot similar to Jupiter's Great Red Spot. The difference with Neptune, though, is that spot disappeared a while back. So the storms are obviously changing a lot, and that's kind of neat too. So that's Neptune. It does have cloud layers and different layers, but again, we don't know much about it. Again, the Voyager spacecraft was the only one to go by Neptune back in the 80s. Neptune does have rings, just like Jupiter, Saturn, Uranus. It's just its rings are very dim, very hard to see. And Neptune has 14 moons, including a very well-known one called Triton. Not Titan, Triton, which is a really, I want to pull it up. Do we have Triton in here? No, we have Titan, but we don't actually have Triton. That's really surprising to me. I thought that Triton would be a really important moon to include. Oh, that's okay, though. We can find it later. At any rate, Triton is a lot like the planet Pluto. It's very icy. We think that it was a captured comet or asteroid, or rather these things called trans-Neptunian objects. There's actually a bunch of objects out past Neptune that form what we call the Kuiper Belt. Some of them actually pass into Neptune's orbit, and we think that Triton, that moon, which is a little bit smaller than Pluto, Triton might have been captured by Neptune as it was going in close. Neptune's gravity pulled on it, gathered it, and now it's now it belongs to Neptune. So I want to try and find the belt of objects out past Neptune. We call it the Kuiper belt. I don't know if we can actually add it in here. It doesn't look like it because these are mostly rings, and I don't want to add too much more to tax the simulation. But we could add Pluto as well. Pluto is not a planet. It is a dwarf planet. So sorry to those Pluto enthusiasts who will inevitably yell at me for that. Don't worry about it. Pluto's not much further than Neptune, but it also has a really kind of weird orbit. And I'm going to try and put it in because it's kind of fun to look at. So see, it's not considered a planet in here. It's going to be considered a different object. Not a moon. Yeah, it's a minor object. Minor planet, I guess you could call it. Sorry about that. I muted the mic so I didn't sneeze too loud. But so Pluto, the best. Okay, so it's 39.5 astronomical units. So right about here. But here's the really interesting thing about Pluto is that it's tilted. Its orbit is tilted pretty far. I don't know the actual tilt, but you can see that the solar system is actually flat. All the planets orbit in their nice ellipses. They're not circles, they're ellipses. Let's go see the sun. So they're ellipses, not circles. And Pluto looks like it's all in order, but as soon as you turn sideways, you can see that Pluto's orbit is tilted compared to the rest of the solar system. And that's true of a lot of trans-Neptunian objects. It's true of a lot of minor dwarf planets that are out there. There's only 5 that we've classified so far. But yeah, they're all tilted compared to the other planets, which are nice and orderly. Now, and that's likely just because Pluto interacted with something a long time ago, another minor planet out in the Kuiper belt. There's a lot of objects out there, about 100,000 known objects in the Kuiper belt right now that are all spread out way out here in outer space past Neptune. So that's it. Wow, that took us about 48 minutes. A long time to create the solar system, but this is basically it. We made the solar system as it is. With all the inner planets really, really close, with our habitable zone, the Goldilocks zone right there. That's where the life can be. It's thought, however, that there might be life in a few other places. Moons of Jupiter, like Europa, moons of Saturn, like Enceladus or Titan. Moons of gas giants could be places where there's life, and that's because the gravity of those gas giants is so powerful. It pulls and pushes on those moons, causes them to heat up, and that source of heat can melt some of the ice that's deep within the planet and create an ocean. And actually, Europa, if we add in the moon Europa is one of those places where there might be life, and that's a place where humanity is really focusing on. Okay, I'm going to pause the simulation there. Europa is a place where there could be life because underneath its surface, that's not a really good texture of it, but it is really cold, and under the surface, about 40 kilometers below this thick ice layer, on its surface is thought to be a liquid water ocean where there could be life. And that's amazing because there's a lot of water, a lot more water than there is on the Earth, and a source of heat. That's, as far as we know, that's what life needs. And so Europa might be the place to look for life in the solar system. And if we found life in our solar system, on Mars, on Europa, on one of Saturn's moons, and here on Earth, and it was distinct, there were 2 separate types of life, that might mean that life is everywhere. Okay, so that's something cool to know. And that's our solar system. That's about all we've got for the stream. I think I'll end it there. So thanks a lot for checking it out. We did a little tour of the solar system that we built ourselves. The program was Universe Sandbox. And come check out other streams. You can find us on YouTube as well, at youtube.com/astroinaction. All these videos will go up there. And you can find the social media there as well for more streams, more recordings, more fun kind of space stuff and visualizations. That's what we do. So check it out. My name's Ryan. I hope you guys have an awesome day. Talk to you again soon.